We proceed exercise 2.2 of relation and function. We do question number 4. Question number 4 is given. The figure is given for question number 4. Question number 4. There are two sets, P and Q, which is given in a figure diagram. P and Q. P has the element 5, 6, 7. 5, 6, 7. 5, 6 and 7. Q has the element 3, 4 and 5. 3, 4 and 5. And it is represented by arrow diagram. So it is represented by arrow. There is a relation from 5 and in between 5 and 3, 6 and 4 and 7 and 5. There are two sets P and Q. Set P has the element 5, 6, 7. Set Q has the element 3, 4, 5. And relation is defined from set P to Q. So write this relation in the set builder form. We have to write this relation in the set builder form. So the first part, write the relation in set builder form. So let the element of set A, set P is X and the element of set Q is Y. Let the elements containing in set P is represented by X and the element containing in set Q is represented by Y. So we have to write this relation in set builder form. So let R equals to ordered pair XY such that Y equals to X minus 2. Y equals to X minus 2. This is X. When we subtract 2 from X, we get the value of Y. This is the value of X and this is the value of Y. So 5 minus 2, we get 3. 6 minus 2, we get 4. And 7 minus 2, we get 5. So X minus 2. These are the values called X and these are the values called Y. So X relation is given, is defined in set builder form. R equals to X comma Y ordered pair such that Y equals to X minus 2 where X equals to 5, 6, 7. Where X equals to 5, 6 and 7. So this is the relation written in set builder form. Now write this relation in set builder form and then we have to write this relation in roster form. So in roster form we write in the way in ordered pair. So 5 comma 3, 6 comma 4 and 7 comma 5. So this is written in roster form. Then we have to find its domain and range. So the domain is found by the first element of the ordered pair is called domain. And the first element of the set P is 5, 6, 7. And range is the second element of the ordered pair is called range. So range will be 3, 4 and 5. 5, 6 and 7. This is the first element of the ordered pair and the second element of ordered pair is 3, 4 and 5. So the range is 3, 4, 5 and domain is 5, 6 and 7. So in fourth question we have given ray diagram of two sets P and Q. The elements of set P were 5, 6, 7 and the elements of set Q were 3, 4 and 5. And the first we have to retain the relation, we have to write the relation in set builder form. So the difference between these two elements is 2, and this is y, this is x, so we write y equals to x minus 2. Then in roster form, then domain and range. Next, question number 5. Let A equals to 1, 2, 3, 4, 6. Let A is given 1, 2, 3, 4 and 6. 1, 2, 3, 4 and 6. Set A is given. And R be a relation on A defined by R is a relation on set A defined by R is a relation on set A defined by ordered pair AB. This relation is defined in set builder form. R equals to ordered pair AB such that AB belongs to A comma B belongs to A, and the condition is given B is exactly divisible by A. B is exactly divisible by A. Relation is given in set builder form. R equals to ordered pair AB such that A comma B belongs to set A and B is exactly divisible by A. So we have to write R in roster form. Firstly, we have to write R in roster form. The first part is this relation we have to write in roster form. And B is exactly divisible by A. So when we take A as 1 and B as 2, then 2 is exactly divisible by 1. 2 is exactly divisible by 1. Then we take ordered pair 1 comma 3. 3 is exactly divisible by A. Then 1 comma 4. Then 1 comma 6. 6 is exactly divisible by A. 4 is exactly divisible by A. Then 2 comma 3 we can't take because 3 is not exactly divisible by 2. So we take 2 comma 4 and 2 comma 6, then 3 comma 6. So this is the relation in roster form. This is the relation in roster form. Also we have to write 1 comma 1 because this is the relation from set A to set A itself. So 1 is also divisible by 1, 2 is divisible by 2, 3 is divisible by 3, 4 is divisible by 4 and 6 is divisible by 6. This is the relation from set A to set A. So the first element A is 1, second element is 1, first is 2, second is 2, 2 is divisible by 2, 3 is divisible by 3. Then second part, we have to find the domain. We have to find the domain and range. So domain is the first element of the ordered pair of the relation. So the first element is 1, 2, 3, 4 and 6. 1, 2, 3, 4, 6 is domain, and then we have to write the range. So second element is the range. Second element 2, 3, 4, 6. 2, 3, 4. 1 is also 1, 2, 3, 4, 6. 1, 2, 3, 4 and 6. So range and domain both are same. Then question number 6. Determine the domain and range of the relation R defined by R equals to x comma x plus 5. The relation is given R in set builder form. Question number 6. Relation R is given in set builder form. R equals to x comma x plus 5. Ordered pair x comma x plus 5. X comma x plus 5 such that x belongs to 0, 1, 2, 3, 4, 5. X belongs to 0, 1, 2, 3, 4 and 5. Then determine the domain and range of the relation. We have to write the domain and range. So firstly we write the relation in roster form. This relation we will have to write in roster form. So x is taken from set x belongs to 0, 1, 2, 3, 4, 5 and x plus 5 we get. So when we take the value of x equals to 0, here we get 5, so 0 comma 5. When we take the value of x equals to 1, we get the ordered pair 1 comma 6. When we take the x 2, we get 2 plus 5, 7. 3, we get 3 plus 5, 8. 4 plus 5, 9. 5, then we get 5 plus 5, 10. So this is the relation which we write in roster form. Now we have to find its domain and range. So domain is the all first element of the ordered pair. 0, 1, 2, 3, 4 and 5 is the domain. And for writing its range, the second element of the ordered pair. So 5, 6, 7. 5, 6, 7, 8, 9 and 10 is the range. 5, 6, 7, 8, 9, 10 is the range and domain is 0, 1, 2, 3, 4, 5. Now we discuss question number 7. Question number 7. Write the relation R equals to ordered pair x comma x cube. Write the relation R equals to ordered pair x comma x cube such that x comma x cubes such that x is a prime number less than 10. X is a prime number less than 10. In roster form. This relation is given in set builder form. This relation which we have given in set builder form, and the relation is R equals to ordered pair x comma x cube such that x is a prime number less than 10, and we have to write this relation in roster form. So the first prime number taken is 2. The prime number from up to 10 less than 10. So 2 is the prime number, 3 is the prime number, 5 is the prime number, 7 is the prime number. So we will put the value of x. When we take the value of x equals to 2, the first prime number, the value of x cube becomes 8. 2 raised to the power 3, 8. When we take the value of x equals to 3, then we get x cube as 27. When we take the value of x is 5, we get 125. When we take the next prime number less than 10, 7, we get 7 raised to the power 3, 343. So these are the relations which is written in roster form. Now question number 8. Let's set A equals to x, y, z. Question number 8. Set A equals to x, y, z. Set A equals to x, y, z. And another set B is given 1, 2. Set B is equals to 1, 2. Then find the number of relations from A to B. Find the number of relations. Relations from A to B. So for finding the number of relations, we use the formula number of relations equals to 2 raised to the power m into n, where m is the elements of set A and n is the elements of set B. So the elements of set A is 3 and the elements of set B is 2. So the answer, the result, we get 2 raised to the power 6. So the number of relations, for finding the number of relations from set A to B, we use the formula 2 raised to the power m into n, where m is the number of elements of set A and n is the number of elements of set B. Now the last question, question number 9. We are given R with the relation on Z defined by R equals to, Z means integer, R be a relation on Z. R be a relation on Z. Z means integer. R is a relation on Z defined by R equals to ordered pair AB. R equals to ordered pair AB such that AB belongs to Z, such that A comma B belongs to Z, and A minus B is an integer. A minus B is an integer. So A is integer, B is integer, and the result A minus B is an integer. So when two integer is subtracted, then again we get the integer. And integer are of two types, either it is positive integer or negative integer. So find the domain and range of R. So the domain and range of R. Domain will also be integer, because domain is the first element of the ordered pair. Domain is the first element of the ordered pair, and range is also integer. Because when we take two integer A and B, suppose 2 and 3, and when we subtract, so 2 is integer and 2 minus 3 minus 1, which is also integer. So domain we get integer and the range also we get as integer. So this exercise has been finished. Now we talk about the function. This exercise was based on relation. Now we talk about the function. Firstly, we understand the definition of function, and also we understand that when the function is defined or when the function is not defined. Function is a special type of relation. Function, it is a special type of relation. function is a special type of relation because relation, a special type of relation means if two sets A and B are given, then function is also the subset of A cross B, and its definition is let A and B be any two non-empty sets. Let A and B be any two non-empty sets. Let A and B be any two non-empty sets. Then a rule or a correspondence F. Then a rule or a correspondence F. The rule is represented by F. Then a rule or a correspondence F which associates each element of the set. Which associate a rule or a correspondence F which associate each element of the set. Which associate each element of the set A, which associate each element of the set A with a unique element of the set B, with a unique element of the set B. Each element of the set A with a unique element of the set B is called a function from A to B. Is called a function. It's called a function from A to B. This is the definition of the function. Let A and B be two non-empty sets. Then a rule or a correspondence F. Function is represented by F. Then a rule or a correspondence F which associates each element of the set A with a unique element of the set B. It's called a function from set A to B. It is represented by F such that A tends to B. Function is represented by, or rule or correspondence F is represented by F such that A tends to B. F such that A tends to B, where A is called domain of the function, where A is called domain of the function, where A is called domain of the function, and B is called codomain. B is called codomain of the function. Where A is called domain of the function and B is called codomain of the function. So it is a special type of relation, and if A and B be two non-empty sets, then the function is a rule. Non-empty sets, then a rule or a correspondence F which associates each element of the set A with a unique element of the set B. It's called a function from set A to B. Let us see by an example. We understand the function by an example. Let's set A equals to 1, 2, 3. Let set A equals to non-empty set, so 1, 2, 3, and set B equals to 2, 3, 4. Set A equals to 1, 2, 3 and set B equals to 2, 3, 4. and we know that function is a special type of relation. It means function is also the subset of A cross B. So we calculate A cross B first. So the ordered pair 1, 2, 1, 3, 1, 4, then 2, 2, 2, 3, 2, 4, then 3, 2, 3, 3 and 3, 4. This we have calculated A cross B. So function is also a subset of A cross B. Function must be made from A cross B. Now let us take a function f1 equals to 1, 2, 2, 3, 1, 2, 2, 3 and 3, 4. 1, 2, 2, 3 and 3, 4. Let function is defined. f1 equals to 1, 2, 2, 3 and 3, 4. So this function is defined from A to B. This function is defined from A to B. f1 is defined from A to B because each element of set A, each element of set A has unique image, in set B. This function is the subset of A cross B, first thing, because every ordered pair is available in A cross B. So f1 is the subset of A cross B. That's why f1 is a relation. And also the every element of set A, the first element 1, 2, 3, which is in set A. So every element of set A has unique image in set B. When we draw the ray diagram of both the sets A and B, so the first element belongs to set A, which is written as 1, 2, 3, and the second element belongs to set B, so 2, 3 and 4. Second elements of the ordered pair belongs to set B, and first element of the ordered pair belongs to set A. And function is defined from A to B, F. So there is unique image of 1 with B, there is image of 2 with 3, and there is image of 3 with 4. Unique image means each element has one image. Each element of set A have only one image in set B. So this is called uniqueness. So this function is defined because each element of set A has unique image in set B. Let us see another case. f2 equals to 1, 2, 1, 3. f2 equals to 1, 2, 1, 3, 2, 3 and 3, 4. 2, 3 and 3, 4. 2, 3 and 3, 4. So firstly check whether it is a subset of A cross B or not. So 1, 2 is available, 1, 3 is available, 2, 3 is available, and 3, 4 is available. Then draw the ray diagram, set A and set B. The first elements of the ordered pair belongs to set A. So the first element is 1, 2 and 3. Second elements of the ordered pair belongs to set B. So 2, 3 and 4. F2 is the subset of A cross B, but it is not a function. Why it is not a function? So let us see. 1 has the image 2, 1 has the image 3, 2 has the image 3, and 3 has the image 4. There is no uniqueness. The element 1 has 2 image, 2 and 3. Since the element 1 has 2 image, 2 and 3, so it is not a function. Since 1 belongs to A, since 1 belongs to A, has 2 images, in set B. So F2 is not a function. F2 is not a function. Because uniqueness is must. There must be unique image. Yes, element 1 has 2 image, 2 and 3. That's why it is not a function. So function is not only a subset, but must be uniqueness. So F1 there is a unique image and F2 there is no unique image, so it is not a set.